Let's begin class. So today you need to examine subsections 4 and 5 of section 4. This is less material than normal because we just got done with that test. Now these two topics are not necessarily ones that are always taught in every time series analysis course, but I think they're good ones, especially the second one. So this first subsection starts talking about what happens if you have 2 time series or even 3 or 4 time series, and you want to examine the relationships between the different time series. And the way that we can start to do that is look at something called the CCF, which stands for the cross covariance function, or you can also say the cross correlation function. And what the cross covariance function is just simply the covariance between, let's say, one time series is denoted by x sub s, where s is the time point of interest, and also y sub t, where t is the time point of interest for y. Notice the notation here. We use the gamma again like we've done before for the autocovariance function. We put an x first, y second, and then we indicate the corresponding time points as s and t. So notice in this expectation here, I actually wrote x first and y first, or y second. So it's just a covariance. We can then, of course, look at the cross correlation function, which is denoted by the Greek letter rho. And so we take that cross covariance function and we divide by the square root of the autocovariance function for x at time s, and then the square root of the autocovariance function for y at time t. Then, similar to what we saw for just one time series, now we're interested in stationarity. And with just one time series for stationarity, you looked at the mean. Is it dependent upon time? Look at the autocovariance function. Is it dependent upon time? Or can we only, let's say, look at the lag difference between 2 different time points? And so we can then look at the extension to this, where we have 2 time series. That's called joint stationarity. And we have 3 conditions associated with it. The first 2 conditions correspond to that I have stationarity for x. I also have stationarity for y. And then the third condition is the joint stationarity, where now this autocovariance function is the only thing that matters there is the lag difference between x sub s and y sub t. Now, with this notation, it's very important that you pay close attention to it. So notice how in the subscript I have an x and a y. I put x first, I put y second in the expectation. And the reason why that's important is because this h here, which again corresponds to the lag difference, goes with that first variable that you're putting in there. In this case, x. The cross correlation function, when we have joint stationarity, then becomes, as you might expect, we only have to worry about that lag difference. Now, the reason why this is such a big deal here, where we put that h, is because we need to understand better what are some equivalent ways to represent the equivalent cross covariance functions when I change, let's say, maybe the order of x and y, or if I say look at a positive lag difference, maybe I look at a negative lag difference. And so the cross covariance function for x and y at lag h is exactly the same as the cross covariance function of y and x at negative h. Why? Well, this then comes to, and I did this in the videos, actually writing out what these symbols mean. Notice how, in what I just wrote out, x is h time points ahead of where y is. Just like what we had here. That's why we have the equivalence. This can sometimes be confusing with students, but as long as you go back to what an expected value is, it actually becomes very simple. Then, if we also look at this, where we have the cross-covariance function for x and y at lag h, that is not usually going to be equivalent to the cross-covariance function of y and x at lag h. And again, from looking at the expected value, you'll be able to see that. And lastly, cross-covariance function for x and y at lag h is not going to be the same as the cross-covariance function for x and y at negative h. Okay? Notice how that's a little bit different from, again, what we saw with the autocovariance function when we use h or negative h. Now, in these set of notes, also what was discussed is, well, how can we estimate the cross-covariance function, then estimate the corresponding cross-correlation function? How can we make inferences about these cross-correlations as well? Just pay special note, especially right here, when we do the estimation of the cross-covariance function, we go from, the summation goes from t equal 1 to n minus h. And the reason why we don't go up to n is because otherwise you will run into particular places where you don't have, let's say, a particular x or a particular y at a certain time point when you're trying to find this, when you're trying to multiply this part out. Now, the easiest way to do these calculations is use programmed in functions that already exist in R. I first introduced the ACF function. I kind of debate sometimes whether or not that is really worthwhile that I should introduce it, because it can be quite confusing, as hopefully what you saw in the notes in the video, understanding exactly what the R output is giving you. The CCF function, what it gives, is much more straightforward, and so I recommend using that. I guess the reason why I still introduced the ACF function is because, well, we've been using the ACF function before. And so the natural, if we can still use it for cross correlations, why not take a look at it? But again, it's a little bit confusing. Now, the second subsection dealt with arch models. And this is one of the few places in my notes where you don't see any R code. Well, you saw some R output, I believe. But not necessarily where I go into details about how to get R to do stuff. And these arch models help provide us another way to take into account, let's say, non-stationarity in the variance. In particular, these models were developed for situations where you have, let's say, periodic, let's say, shocks to a time series, meaning that at small, maybe time points, every once in a while, you have a lot of variability. And the classic case where this occurs is with respect to various financial stock indexes, where, let's say, over a week period of time, or maybe even a couple weeks period of time, where there's a lot of uncertainty because of problems that are happening with the economy. That can cause stock prices to go up quickly or go down quickly. And that's what these models help to take into account. And basically, these are often used in situations where you have what otherwise looks like a white noise process, except for that variance changing every once in a while. And what one can do is actually look at the square of the time series to see that, well, it doesn't have, if you look at the ACF and PACF of the square of the time series, it no longer has these non-significant autocorrelations or partial autocorrelations anymore. You see that there's some dependence in the squared values. And so, in order to write out one of these arch models, there's two main ways that you'll see people write them out. The first way is something like this. And there's extensions to these kinds of models I'm introducing here that you'll learn about in the next set of notes. So if, let's say, x of t was just white noise, we would represent it as x of t is equal to wt, or if we allow for the mean to be different from 0, x of t is equal to mu plus wt. Where I don't know what happened there. Let me put that back in there. Where wt, white noise, distributed independent, means 0, but actually it's not quite white noise. We're going to allow that sigma square that we normally have there to be dependent upon t. So it allows it to change as a function of time. Also, if we define y sub t as equal to xt minus mu, just simply so that we have a mean of 0, we can write this sigma squared t then as a function, a linear combination of parameters denoted by the alphas and these y's squared. Okay, so this allows now this sigma squared to depend upon what has occurred in the past. Notice how this is sort of like autoregressive kind of model situation. That's where the AR for arch models come from. Now, another way to write out the model is like this, where we just say y sub t is equal to sigma t times epsilon sub t, where y sub t has a mean of 0. So it's just like our data, but it's already been adjusted to have a mean of 0. The sigma squared t is exactly what we had before. And we say our epsilon sub t is distributed independent, mean 0, variance of 1. Okay? Now note then that this y sub t then, of course, would be independent, mean 0, variance sigma squared t, using what you would learn in a mathematical statistics course. Now, very often, this y sub t is actually not necessarily your observed data that's adjusted by the mean, but it could be your first differences with respect to x sub t. This happens a lot with financial time series. It could be, let's say, 1 minus b times the log of x of t. Or it could be 1 minus b times x of t divided by x of t, where we have essentially like a rate of return. That was discussed in the notes. Okay, so that was a brief introduction to arch models. We have, I think, 3 other sections of notes, or no, 2 other sections of notes that talk about these arch models further. So don't worry if maybe some of that's not quite clear yet. You know, we have more notes on it. Are there any questions regarding the corresponding material here for today? Excuse me. Okay. Let's talk about the tests. Test scores were quite good. Average score was 92.6. We had a rather small standard deviation, 3.1. All students in the course got between 80 to 100%. So that's great. Still, look at my answer key that I provided. It does give you some additional feedback on these problems, more feedback than what I would, let's say, write on when I grade your tests. Now, there are some problems I do want to talk about regarding this test. The most missed part of the test was number 1C. Okay. This is where you needed to find the variance of the forecast error. Now, in the project number 3, and also 4. Well, I think it was mainly 3. I noticed a number of students trying to find the variance of the forecast error when you had to actually derive it. They tried to derive it a different way than I was doing in class, or in the videos and in my notes, in terms of I always would write everything out as an infinite order moving average. Now, generally speaking, the students in the project were getting it right, so that's fine if you get it right. There's often more than one way to derive this stuff. But I believe I often put a note, say, well, it's like, see my answer key for this other approach. And the problem then that occurred on this test is that it was a little bit more difficult to use this alternative approach in deriving. And this led to students getting it wrong. At least this, again, was the most missed problem on the test. So let's just briefly talk about this problem. So what we have is a ARMA 1-1. And I think what made it more difficult for students is that we observed 200 time points, and rather than maybe just going to the first time point in the future, we went 2 time points into the future. And so the way that I approach this, the way that you'll see others approach this outside of this class, you'll see this in textbooks, is you always write it as an infinite order moving average. And so basically you end up with this part right here. Do a little bit of math, multiply stuff out. And for this particular problem, there was only one of these sides that you actually needed to figure out, because we only were going 2 time points into the future. It ends up being just phi 1 plus theta 1. Now, the general expression then for one of these variances ends up being then the forecast error variance. Sigma squared W times the sum from I equals 0 to m minus 1. M in this case is 2, so I just need to do my sum up to 1. What does that mean then for us? Well, we have sigma squared W times psi 0 squared plus psi 1 squared. This psi 0 is always 1. So now we have this psi 1. You can just simply put it right in there and get the variance. Now, because I was seeing many students approach this a different way, or this alternative way, I actually wrote up then what would the derivation look like with this alternative method. And I think, as you can see here, and maybe I'm just showing too many steps, but look how much longer it is versus what I did up there. I think the number one problem that students were having to get this right is that at some point, where was that? When you needed to include what was in the past. Let's see here. Yeah. So here's X201. Students were not necessarily including it correctly. And then also they were not necessarily including what was the previous forecasts for m equal 1 in this expression correctly. And that's what screwed up getting the final result. So while you're welcome to continue doing it that way, I hope you agree with me that it's probably best to write everything as an infinite order moving average. Any questions about that? Well, one small thing. This particular problem asks for the estimated variance of the forecast error. Not the variance, the estimated variance. And so that means then you needed to go one step further after you derive then this variance. You need to make sure it is represented as the estimate. So in other words, you put the hats on the appropriate quantities. So I put a hat on top of the var. I put a hat on top of all the parameters. That's all. And, I bring this up because, I was a student once, and I know it can be somewhat difficult sometimes to fully get all the notation and stuff like this. But, it's like, let's say, let's relate it to something else that you've seen. So in another class, you talk about the variance of x bar. Also talk about the estimated variance of x bar. What's the difference between the two? Well, this is sigma squared divided by n. This would be s squared divided by n. Okay? And there's a big difference there. One is a quantity represented by a population parameter. One is something you can actually calculate from a sample. Okay. So 2A and 3B had the same issues sometimes for students. Let's take a look at 2A here. Let me make this a little bit smaller. Okay, so what we have here is some data that has some seasonality with it. And I asked for complete a plot of the estimated autocorrelation function, and the plot will suggest some type of differencing is needed to take care of non-stationarity mean. What is this differencing? Well, the differencing, I think pretty much everyone got it. Obviously, we're seeing this pattern of every 7 lags, where we have these large, we see a pattern that kind of duplicates itself for every 7 lags. But what students were often saying, let's see if I have it. They were saying, okay, I need to take first differences with respect to a season of 7 because I have significant autocorrelations every 7 values, every 7 lags. And indeed, that is correct. We are having these significant values every 7. But that's not the reason why we need to take first differences with respect to the season. Rather, the reason is because we have very large estimated autocorrelations at every 7. That's the reason. And while if you have very large autocorrelations, you're very often going to have significant autocorrelations, it's the fact that they're large. That is the important thing, not the fact that they're significant. Then on 3, let's see, on 3, let's see here. Then 3B, this was a problem dealing with the RFEMA situation. What should the estimated ACF for X T look like when RFEMA model is appropriate for observed data? Again, many students were focusing on that there were significant autocorrelations. Not necessarily that they're large autocorrelations, but they're significant. Again, that's not the thing that you look for. It's just the fact that you have moderately large estimated autocorrelations that persist for a very long number of lags. Not the fact that they're significant, which most likely they will be significant. It's the fact that you have moderately large ones. And then lastly on 3D. So this was another seasonal one. So describe what the true ACF should look like when X at T comes from this particular SARIMA model. I had meant to actually put PACF in there as well, in addition to ACF. Of course, I just graded you on the ACF because I didn't put PACF in there, but I did leave the answer as is in terms of the PACF was there. Now, the common mistake that students were making was that they were interpreting this as if there was a 2 here and a 2 there. So I would, for more than one test, students would say that, okay, the ACF is tailing off, which is correct. But they say the tailing off starts after lag 2. That only happens if you also have a moving average component. So since we don't, the ACF actually starts tailing off right at lag 1, or the first seasonal lag 12. Okay? So don't get confused by that. That incorrect interpretation was only if we would have had a moving average component to the model, which we do not. Okay, sorry to focus on negative stuff with regards to this test. Again, the test grades were really good, but I bring this up because I want all of you to get 100%. And these are some small things that I had noticed from more than one student, so that's why I bring this up in class. Now, as a reminder about how final grades are calculated. So we have 2 tests in this course. I'm not talking about the final exam. I'm just talking about the 2 tests during the normal part of the semester. The highest test grade that you got is 40% of your grade. The lowest test grade is just 10%. So you can think about now about where you stand in this class. To help you out as well, later this week, I will post what I have as your current grade in the class, so you can see where you better stand. And you should be able to calculate this yourself, but I will post this too. I will also post all of your other grades that you've had so far this semester, just to make sure that I've recorded it correctly, and it gives you an opportunity to double check my work essentially. Now, with respect to the final exam, in all my courses when I do a final exam, I like to look back at the previous tests. What were problems that sometimes, let's say more than one student, what were they getting incorrect? What were they having difficulty with? And since I want you to learn from those mistakes, I will often put some of those same types of problems then on the final exam. So we just talked about common issues that were occurring with test number 2. You can go back to our discussion for test number 1 as well, common issues that were occurring. Just make sure you, let's say, study a little bit longer on those particular issues that I brought up, so that the same mistakes are not made a second time. Okay, so that's all the comments I have about the tests. Again, they were very, very good. Were there any questions about it?
Can we go to the drift term?
I'm sorry?
The drift term explanation.
Sure. What problem? Oh, yeah.
Problem C.
Yeah.
I don't get it. Why being a non-stochastic trend is beneficial to this?
Well, the key is that, a lot of people would think that once you take those differences, you have no trend. Trend is in terms of, let's say, going up or going down. You wouldn't have that. But what Shumway, Stouffer, and others will say is that, they've noticed, let's say, with actual observed data, even after you take those first differences, you can still see some stuff that's going up or some stuff that's going down. And this drift term helps to account for that. I mean, as I said, this is
the noise that is remained to be explained.
Say that one more time, please.
That is just the noise that we couldn't capture, or the estimated mean couldn't capture and left over.
Well, I guess this is essentially still information that you would not normally be able to capture. But this information has some kind of, let's say, a non-statistical way of putting it, another weird aspect to it. That things are still, let's say, going up, or things are still going down in like a linear manner. And that's what this delta allows you to take into account.
Yeah, I tried one model with and without the drift drum, and I could see that the sigma squared W decreased, and the variance of the forecast, they also decreased. I don't know if that is.
So are you saying that you try to actually simulate?
Yeah.
Okay.
In one of the data set from the course note, ARIMA 111.
Mm-hmm.
So I included the drift drum once and not included the drift drum once, and saw that the variance got lower and the forecast variance also decreased. With including the drift.
So you actually, let's say, looked at a plot of the data over time, and you thought the variability was decreasing because of the drift drum?
I fitted the model.
Okay.
With the drift drum.
Mm-hmm.
Saw that variance was lower. Then
Okay.
computed the forecast and calculated the standard error of the forecast. That was also decreasing.
Okay, so you were making a comparison to with the drift term,
Yeah.
without. And I guess it does make some sense that there would be a smaller sigma squared with the drift term if the drift term is important, because you are now accounting for this other information that you weren't before. I guess I never actually have even thought of even looking at that, but I think it makes sense. Like, how much was it less? I'm just curious.
It wasn't much, but if the drift drum is significant, then I think the forecast we would include that, and the forecast would be better.
Well, I agree, because you're accounting for some additional information, so there's less unknowns, and so intuitively you would expect your forecast error to be smaller. Yeah, I think that makes sense for that to happen. Yeah. Other questions? Okay. So there's just two others, well, actually three other things that I want to talk about here today. First of all, so I really like using a hybrid format to my teaching. And, the first day of class, I guess the second time we met, I talked about this a little bit. I've done some assessments, actual numerical assessments, and have found that students, in terms of their grades, tend to be right at the same level as if I were to teach this, let's say, using a standard way of teaching versus if I were to use a hybrid blended learning format of teaching. And at times, student grades are a little bit higher. And this matches also some research that was done by a now retired economics professor at UNL. But a complaint that sometimes that I get from students is that with the blended learning or hybrid approach, you actually have to do more work than what you would do with a regular class. And there's different ways to, I guess, quantify work. One way that I like to use when I'm teaching is, well, if you were to actually attend this class in a regular format, you would be in this classroom for 37.5 hours during the semester, excluding the final exam. That's based upon 15 weeks, 2.5 hours per week. Well, let's think about now what the equivalent would be for a blended learning format. if you go through my videos, you will notice that there are 19.6 hours of videos. And, I'm expecting you to watch those videos before we come to our Tuesday class. We had 2.5 hours on Thursdays for tests. If you really want to, you can include the extra half hour, essentially, that I gave you for the test to make it 3.5. It's up to you if you want to. But 2.5 hours. And then in terms of these Tuesday classes that we have, through week 13, which is our last week, or that was last week, we have 13.4 hours of these Tuesday classes, on average about 67 minutes per class. And so if you add all this stuff up, this ends up being right now, we are at 35.5 hours. Compare that to 37.5 hours there. So what that basically means that we need to average about 60 minutes for today and next Tuesday to be essentially at the same level as what you would get if we were to do a standard format for this kind of course. And so that's why I think that in terms of the number or the amount of work, let's say, that you have to put in a course like this, I think is equivalent to if I were to teach this in a standard format, at least through this measurement here. So it's just an interesting little tidbit about these kinds of teaching formats. I mean, I think there's other benefits as well. I know not necessarily everyone agrees with me, but especially at the graduate level, here this format gives you more flexibility. You can essentially watch the videos wherever you want to. You can come to the Thursday classes if you need help. I think having it at that particular kind of a time where you need help is, I interact a lot more with students that way than I would if I was teaching a standard format and just simply had students come by for office hours. I've actually tracked that. That's why if you notice on Thursdays, I actually track the number of students who come to our classroom here every day, just as a way to show that, that would be a lot more than when I've tracked how many students actually stop by my office hours during a normal class. So just a little information there. So the second of the three things I want to continue with today is I want to talk about course evaluations. If you've had me for a course, you're going to see that this course in the past, this discussion here is going to be very similar to what I've discussed then. So with course evaluations, of course, there is a regular course evaluation that you do in all your courses where, if I come over here to Canvas, I come down, at least my screen is going to look a little bit different from your screen, and eventually you're going to get instructor course evaluations. You click on it and it allows you to actually do the course evaluations. Now, I would assume that probably all of you maybe got emails, maybe Saturday or even Monday, saying that the course evaluations are now available. Does that sound like that's what happened? Okay. So this is the standard way that course evaluations are done for our department and many other departments as well. You have until the Saturday before finals week to complete those particular course evaluations. I want to just emphasize that these are truly important. Please, please, please take the time to do these course evaluations. This actually is the only way that the department actually evaluates my teaching. I wish there was more, but this is the only way that it's actually done. Now, I also like to bring this up because I'm a fully promoted professor. I'm a full professor. And so compared to, let's say, an assistant professor or associate professor, maybe these course evaluations are not as important. But for your other courses, especially when you are taught by an assistant professor or associate professor, these are extremely, extremely, extremely important. To give you an idea of this, so I am the chair of the Promotion and Tenure Committee for my department. And so we are the ones that provide an evaluation of our faculty every year regarding how they're doing. And especially when a person goes up for promotion, we actually have access to every single student evaluation that they received. And we, or at least I know I do this, I look through every single one. I look at every single comment that a student made. These course evaluations then also are made available to other people outside our department who eventually will evaluate these assistant and associate professors for promotion as well. When I was assistant and associate professor, we only had paper-based ones back then. I had to turn in every single student evaluation I ever had. I would have a binder like that thick of course evaluations. So these are truly important. Obviously, if there's a problem, the course evaluations are a place that you can mention a problem with the teaching. But don't always focus on the negative things. Don't forget about the positive things. Those mean a lot to us. If we see that a student really likes how this professor is teaching, that the professor is explaining the material well, this professor is providing a lot of additional materials to learn, put that in there. This is helpful for us when we evaluate faculty. So, for my own evaluation, if you liked having, the discussion board wasn't used a whole lot this semester. If you like the discussion board, if you like having typed notes rather than, let's say, me writing on the board and you trying to keep up with my writing, I can write pretty fast. And trust me, you wouldn't be able to keep up with my writing. If you like having typed notes, if you liked having these R programs, like the videos, the website, make sure you mention this stuff. Because if you like this, again, other people will still read these evaluations. If you like this, these other people who read these evaluations might think, okay, well, maybe we need to encourage faculty to, include like videos in their own teaching. And especially if you like this course format, make sure you say that. Now, there's also a second course evaluation that I want you to do. This is a course evaluation that I come up with myself, and it is used in place of our normal week number 15 quiz. This is something you're required to do. I'll show you the questions on it shortly. Please note that it is anonymous. So if we actually take a look at the quiz, I make sure that all submissions are kept anonymous. If we look at the questions on it, the first question is the most important. I will be answering the remaining questions. So even though it's anonymous, if you don't feel comfortable answering the questions, then fine. Don't answer the questions. Just put no there, and you will receive this 5 points. It's still a 5-point quiz, just like all the other ones. You'll receive all credit for it, and you can be done. I encourage you, though, to put yes there and answer these corresponding questions. Excuse me. So, first question simply, what grade do you expect in this class? Second question, what grade would you give the course? In terms of the topic and stuff like that. Where the third question then is, what grade would you give me as an instructor? A, B, C, D, or F? And then I have some other questions. What are some aspects of the course that you think would be good to continue for future semesters? I really, really like teaching. I want to improve my teaching. I want to know what I'm doing well, as also I want to know areas where I need to improve. So, if there's aspects of my teaching that you thought went well here, hey, mention them here. What were some aspects of the course that you think could be improved upon future semesters? Put that there too. I do read through all comments. Also here, There's obviously probably going to be some duplication with this course evaluation, with the other course evaluation, the normal one. That's okay. It's okay to say something twice in your writing up stuff. Next, approximately what percentage of the time for the pre-recorded videos did you watch during the course? So I'm talking about these 20 hours of videos that are available essentially through YouTube on the section materials webpage. So if you say 90%, that means you watched 18 hours of it. I want to know how much these videos are being used. I use this as just a measure of, are they important or not? I will say that some faculty don't believe that videos are useful. And if I say, okay, well, my students on average said that they watched 18 hours of these videos, I can say, looks like the students are using that, and that they shouldn't necessarily just rely on, let's say, some notes posted to the web as their only tool for learning. Then lastly, there are two main methods that I've used for teaching this course in the past. One is what you saw here today. I've used this now the last 2 times I taught this course. All the previous times that I've taught this course, I taught it in a more traditional manner, where we met in the classroom 37.5 hours during the semester. We would go over the material, somewhat similar to what you saw in the videos, where I would just have the notes up, and we would discuss then the corresponding notes during class. However, this traditional format, though, does not allow enough time, though, to go over some other stuff that we did, like, for example, during these Tuesday classes. And there's some stuff I can do, but a lot of it I cannot. These additional examples, like I probably wouldn't have been able to do the UNL enrollment example, just to give you some perspective. I wouldn't have been able to do the AIC Monte Carlo simulation example. And also there'd be less time to go over projects and tests and to review for projects. To review for tests as well. And so simply, here are 2 teaching formats. Tell me which you prefer. And if you want to, you can provide additional comments about which, what or why you made that choice. And I don't know why, but Canvas shows that this is worth 1 point. It is not worth 1 point. The only thing that's worth any points for this quiz is this particular question right there. Okay, 5 points. Okay. So please, this quiz is required to do. It's due the normal time, next Tuesday at 8 p.m. Please take the time to do this, and also the other more traditional evaluation. Okay, any questions? So the last thing is not something you're going to be tested over. But, whenever there's a time in any of my courses where what I am teaching in my course can be connected to something that you will see in another course or another setting, I like to do that. And that's what I'm going to do here, probably for about the next 5 to 10 minutes. And that is, how is time series analysis used to understand Bayesian statistical methods? I'm not saying that we're going to look at how can I, let's say, estimate a model, like an ARIMA model using Bayesian methods. We're not going to do that. But time series analysis, you may not know, really actually fully understand that, is actually used as a fundamental part of Bayesian analysis to understand if things are working correctly, you could say. So I understand that not all of you would necessarily have a background in Bayesian methods, but for those of you who are taking Stat 883, I would assume, first year students who are taking Stat 883, have you seen the Bayesian part of 883 yet? So I'm looking at, I think some of the students you have. Okay, good. So I think pretty much everyone at least has the basic understanding of what Bayesian methods are. Could someone tell me then what's the difference between frequentist and Bayesian methods? A good way to start is, how does the name frequentist come about? Why do we call it frequentist? I'm going to put a note on this. On PhD comprehensive exam, put the question about compare frequentist and Bayesian methods. So, frequentist. Let's think about how we interpret a confidence interval, for example. You go out and you take a sample, you calculate the confidence interval. How about then you go out and take another sample, you calculate a confidence interval. How about you go out and take another sample, you calculate the confidence interval. Let's say you do this 1,000 times. If you're doing 95% confidence intervals every single time, you expect 950 of them to contain the true parameter that you're actually trying to estimate. So notice our interpretation here relies on you're frequently applying the sampling idea. That's how the idea of frequentist comes about. The parameter that you're trying to estimate is a fixed quantity. It does not change. For example, there's one population mean. That's it. Now, Bayesians think about this in a different way. They say, I don't know what this population mean is. I don't know what this parameter is. And as one of my professors said it so nicely when I was a student, those kinds of people say we should represent all uncertainties by a probability distribution. Meaning, this mu is a parameter, but let's actually assume that it has a probability distribution to it because we don't know what it is. We don't know what the exact value is. So we're going to attach probabilities to possible values of that parameter. That's the way the Bayesian will think about these things. And so if we think of this in a general context, let's say that I just have some parameter of interest. We're just going to call it theta. It's not connected to a moving average parameter or anything like that. And we are going to observe a random variable x. That's going to give us information about theta. Then what Bayesians eventually come up with is what's called a posterior distribution. That symbolically could be denoted as f of theta given the value of x. So this is going to give me probabilities associated with what possible values of theta could be, given that I have this information about observing x. So then how do we estimate theta using this probability distribution? Well, it kind of makes sense that one could use, for example, the mean. And that's typically what in a STAT 883 course you learn about. You learn about how you can use squared error loss and show that the mean of the posterior distribution ends up being a nice estimate. You could use the mode of the distribution as well, and that's very closely related to maximum likelihood estimation then. Then I could use the mean to come up with a point estimate, but we know that that doesn't mean that's the true value of theta. It means it's a very likely value of theta. So instead what we could do is form an interval estimate so that we have let's say a 95% probability that theta is between a lower number and an upper number. So this is kind of like the Bayesian version of a confidence interval. But it has the extra interpretation of I do have a probability associated with one particular interval, the probability that that interval works, that it contains the parameter of interest. And so there are different ways to do these intervals. One is called, they're all called credible intervals. One way to do this kind of interval is what's called an equal tail interval, meaning simply you could get, let's say, the 0.025 quantile from this distribution, get the 0.975 quantile from that distribution, and voila, you have a credible interval. There are another kind of intervals called the highest posterior density interval as well. We won't get into that. So this posterior distribution is really what Bayesian methods are really centered on, because this is going to allow you to make inferences about your parameter of interest. The problem is that these posterior distributions are difficult to derive. And so while Bayesian methods and frequentist methods both have been around for a very, very long time, it wasn't until the 1990s when computer power started to catch up or was at a sufficient level that one could start using computer power to not derive these posterior distributions, but instead use computer power to take a sample from this probability distribution and use that sample as a summary measure to calculate the sample mean of all these sample values, and that's your way of estimating theta, essentially. So let me say that again. So posterior distributions can be very difficult to derive by hand. And so because of that, what people turn to using is, instead of deriving it, how about we just take a sample from this distribution without actually even specifying exactly what that distribution is. We take a sample and use that sample to summarize information about our unknown parameter theta. Okay, now we're getting into where time series analysis will be eventually used. Now, the way that the sample comes about is different from what you're used to seeing, where, like a random sample. Where, let's say if I were to, sample, let's say I have a population of size 1,000, and I just randomly choose one item in that sample. I randomly choose another item in that sample, another item in the sample, and so on. That's a random sample. But instead, how this sampling is done is with a non-random sample. Meaning, the item that I choose here was somewhat connected to another item that I chose before. So there's a correlation. And so the most widely used ways to do these non-random samples is using what are called Markov chain Monte Carlo methods, or MCMC. And what you end up with is this. You get a series of sampled values for your parameter that you're trying to make inferences about. Where this, let's say this theta 2 is going to be now not independent of theta 1, but dependent upon what you previously got for theta 1. So this index here is actually, I got theta 1 first, I got theta 2 second, I got theta 3 third, and so on. Where theta 2 is dependent upon theta 1, theta 3 is going to be dependent upon theta 2, theta sub, let's say, b, our last value, is going to be dependent upon theta sub b minus 1. When you have that kind of dependence there, that's referred to as a Markov chain. That's where that comes from. The Monte Carlo comes from the fact that I'm taking a sample. I'm simulating with a computer. So what we have here, since we have this sample, and things are done, the sampled values come about consecutively, we have a time series. So that's the connection with Bayesian methods. With Bayesian methods, you use these MCMC methods, and you come up with a time series as your sample. And one of the most important questions that someone who's doing using Bayesian methods has to answer is, we refer to this often as a chain, not necessarily a time series, but a chain, because of the Markov chain name there. Has my chain converged? All that basically means is this sample that I got, is it truly representative of the probability distribution f of theta given x? Meaning, let's say that this was my posterior distribution. Okay? And I'm going to get sampled values, which I'm going to denote by x's. And since I have a higher area underneath the distribution right here, I'm going to get more sample values here. And my hope is the chain has, let's say, visited all parts of the distribution in an appropriate manner. If that has happened, my my chain has converged. That's what the meaning is. But instead, if I had something like this where parts of the distribution were not being visited by this chain, then the chain has not converged. And that wouldn't be a good representation of my posterior distribution. So, sorry. And so, essentially what we're asking is this series of values that I got, do I have stationarity with them? And put it into a time series context. You'll see that when we get to this next example. So for those of you who took my Study 75 class, you might remember a place kicking example that we often talk about. I'm going to briefly talk about that here. Basically, all of you have seen logistic regression before, and what I would like to be able to do is estimate the probability of success for a place kick in the National Football League as a function of the distance of the place kick. And so here's my logistic regression model. The logit of pi is equal to beta 0 plus beta 1 times distance. Distance is my explanatory variable, my independent variable. It could be like 30 yards, 40 yards, and so on. And I have these parameters, beta 0 and beta 1 there, that I want to estimate. In my Study 75 class, we talk about a frequentist way to do this. We could also use Bayesian methods as well. And so basically what I want to do is get the posterior distribution for beta 1, given my observed data. Get the posterior distribution for beta 0, given my observed data. We don't need to get into the exact details of all this, but I have a sample of 1 year's worth of place kicks from the NFL. And I'm going to use MCMC methods to obtain a sample of 5,000 beta 0s, 5,000 beta 1s, and then summarize that sample to make judgments about what this model would give me. And so here's what you typically see for standard output then in R, or actually other software packages, to demonstrate what has happened during the sampling process. So what we see on the left are histograms of all the beta 0s. So this would be beta 0. This would be beta 1. And let's just look at beta 1. And so we can see that it looks like the center of this histogram is right about here. So probably the mean's right about there. So that means my estimate for beta 1 using Bayesian methods would be something like 0.115, maybe 0.118 or so. Okay. But what we see here on the right side is something that we see in this time series class a lot. A plot of our data over time. I shouldn't say instead, but what we have here, time on the x-axis, which represents the order that I got these betas from. So beta 1, the first beta 1, the second beta 1, the third beta 1. And then we have the actual value of beta 1 then represented on the y-axis. In our class, we would often draw points for each of the values of in this case, the beta 1s. I don't do that here because we have 5,000 of them. That would just really clutter up the plot. But what we see here is actually every beta 1, that sample, is actually connected by a line. And so what we do in a Bayesian methods, or in a Bayesian context, is we look at one of these plots. What we're looking for is, does these values tend to stay in about the same location over the 5,000 sampled values? We don't want to see, sometimes it's just easier to show you something that you don't want to have happen. So if I saw something like this, in a time series context, we would say we have non-stationarity in the mean. In a Bayesian context, this would cause us a lot of worry about, did this sampling process work out? But what we see here in this plot it seems like everything seems to look nice. If we saw this in a time series plot, we would say, hey, we have stationarity. And so based upon what I see in this plot then, I would say that I've had the chain has converged. Now, another plot that's often shown with Bayesian methods is something that looks like this. This is an estimated ACF. So what this looks at is, okay, what is the autocorrelation between, what's the autocorrelation for lag, let's say 2, or lag 5? Meaning, if I have a difference of 2 in terms of that subscript for that parameter I'm trying to estimate, in terms of the time point that they are sampled, what is that association? And so what we see here is at lag 0, now this plot's drawn a little bit differently than what we would. At lag 0, of course, I have an autocorrelation of 1. Now at lag 1, my autocorrelation is about 0.45. Lag 2 is about 0.21, and so on. Notice how these autocorrelations are tailing off. This is something that you want to have happen with Bayesian methods, because the opposite, again, sometimes it's easier to talk about what if you don't have this. The opposite, if you have lots of high autocorrelations for a large number of lags, what that says is that you might have something that looks like this, where essentially the chain is getting stuck in certain areas of that probability distribution. But what we see here is that these autocorrelations tend to go to 0 rather quickly, and therefore I have more evidence of convergence of the chain. Okay. So, I understand not all of you have necessarily seen MCMC methods before. I strongly encourage you to take Bayesian classes out there, because this is very important in statistics. We do have a Bayesian course in our department that's offered spring odd number years. Maybe some of you took our Bayesian course last spring. These are good methods there. And if you're not familiar with MCMC methods, hopefully if you do take a course like that, if you have exposure, let's say for those of you who are stat majors, exposure in stat 822 or 823, hopefully you'll say, oh yeah, that's what Chris was talking about then. Now, a little bit of a side note is that well, first of all, are there any questions about this? At least for some of you, did this kind of look familiar? Have you seen these kinds of things before, maybe, if you took the Bayesian course? Or, 822, do you do stuff like this? Maybe, maybe not. No? How about for those of you taking 823? Do you do some stuff like this at all? Okay. Well, it's good to get this kind of exposure. So if you're able to, and take that Bayesian course that's in our department. Now, I will tell you, even though I talk about all this Bayesian stuff here, I prefer frequentist methods. Why? Bayesians have that extra assumption. They have to actually, we didn't get into all the details there, but they have to actually make an assumption about a probability distribution for this unknown parameter. And they can say stuff like, oh, it's not very informative what they're assuming, or it's not that restrictive. You're still making an extra assumption that a frequentist would not. When do I use Bayesian methods? I only use them when there are no, let's say, good frequentist methods that would work for a particular problem. Because of this extra assumption that Bayesians make in terms of the probability distribution for the parameter, that extra assumption allows them to do, let's say, more stuff than a frequentist could. And they might be able to do the same stuff that frequentists could too, but sometimes it can be easier in a Bayesian context. So Again, I am not a Bayesian. I prefer not to use them. I only use them when I absolutely have to. This example that I just talked about is actually in the second edition of my categorical data analysis book. The first edition also contains a very similar example, but I use a different MCMC method than what I did here. Okay, so we are basically pretty much out of time. So let's talk about what's next in our course. I will be available for questions after class, like usual. You do have that quiz that's due at 8 p.m. I will have my usual office hours. We'll do the usual help class on Thursday. I understand we don't have a project, so perhaps it's not as desirable to come to class on Thursday. But hey, I will be here. So if you want to just come, we can talk about time series analysis, of course. But if there's something else that you want to talk about, we can talk about that too. Next Tuesday, I have my usual office hours before class. We'll have our 9:30 class. For next Tuesday, only do subsections 6 and 7 of section 4. And this is listed on the schedule webpage. The reason why I want to emphasize that is I actually have some additional notes and additional videos for subsections 8 through 9. We're not going to do those here, simply because that would be too much for the last week of class. So that's why I did this to the last time I taught this course. I give you the notes, I give you the videos. So if you're interested in what's discussed in these subsections, you're welcome to take a look at it, but you are not responsible for it for a test. Now, subsection 6 gives you the first example where how you can actually estimate these arch models with R. Subsection 7 shows you how you can combine the arch models with ARMA models. Corresponds to section 5.3 of the book. We will also spend a lot of time talking about the final exam as well next Tuesday. And you do have that quiz survey due at 8 p.m. Lastly, our final exam is Thursday, May 16th at 10 a.m. Okay. Any questions? And that is all here for today.